Transforming your homeschool physics student from confused to confident problem solver is easy if you have the right formula. In this video, I'm going to share the method I've used over 35 years of teaching to help my students go from a novice problem solver to the expert level and be able to grasp concepts that they once thought were totally impossible. Hi, I'm Robin with Centripetal Education. And over the 35 years I've been teaching physics, I've noticed a couple of things that our schools do that really limit our students into what I call a novice problem solver. We all start at the novice level. It's what we do after that that will define who and what we become. So what do I mean by a novice problem solver? Well, the novice problem solver looks at the problem and they try to figure out what equation fits what they've got. They jump right into putting equations down on the paper and putting numbers into those equations immediately. They try to apply very rigid, memorized procedures to every problem. And when it doesn't work, they get frustrated and they want to quit. So how do we take the person in that scenario and give them the skills to be the expert problem solver? There are a couple of things that advanced problem solvers or expert problem solvers have in common. They start, when they look at the problem, the first thing they try to do is come up with a qualitative explanation. They try to look for the qualitative solution. We have two different types of analysis we can do in a problem. We have qualitative and quantitative. Quantitative sounds a lot like quantity, which is a number. So a quantitative assessment is one that's going to rely on the numbers immediately. This is what a novice problem solver is trying to do usually. The expert problem solver looks at it qualitatively. They put it into words. They may talk to themselves or just think through the process as they're going, but what it's doing is they're aligning their thoughts and looking at what they've got, aligning their thoughts on where they need to go to, what things do they have to look for, what things might they have to derive. So they're putting all this together in words. By doing that, they have a very strong idea of what principles or concepts they're going to need to use to make it work. Often they're going to create simplified models of the problem. This could be in the form of a drawing. For example, if you're doing something with a lot of forces acting on an object, you might just do a box with all the forces acting at one time from the center of mass. Very simple drawing, but it allows us to see all the information quickly. It might be a graph. Maybe we graph out the situation. We look at what's happening with emotion. They're going to develop a complete roadmap of how they're going to start, what's they're going to have to do in the middle, and what they're going to get to at the end before they ever start putting numbers into an equation. And the other thing they're going to do as they're making their way through things is they're going to be constantly looking at it and evaluating it. Is this right? Does this make sense? If we're dealing with a car, does the car really have an acceleration of 3,000 meters per second? Does the car really have an acceleration of 3,000 meters per second squared? Okay, if it doesn't make sense, they know they have to stop and go back and look at something that they just did for an error. They're constantly checking their work. I'd like to share with you a very simplistic framework of how this can be done. And I think of the acronym CAME. C-A-M-E. C is for the comprehension phase. We're looking at the problem, we're analyzing it, we're trying to understand what we're doing, where we're going, and basically coming up with our roadmap. The A is for the analysis phase. And this is going to be where we're going to go through and figure out what fundamentals or what concepts we're going to be applying and using throughout the problem. We're going to consider any constraints or things that we're going to have to make an assumption on. We're also, in this stage, we're going to be coming up with our roadmap of how we're going to make the progress from point A to point B. And we're probably going to come up with, and the last thing we're going to do is we're going to work on a coordinate system. of how we're going to define things. Now, this by itself is a major different. This by itself is a differentiating fact between physics and math. In math, we deal with the x and y axis, and they're always the same. X is always a horizontal, y is always vertical, but that's not always the case. In physics, we can solve problems from multiple points of view. And as the observer, I get to pick my own coordinate system. And sometimes the coordinate system I want to pick is not horizontal and vertical. It might be on an inclined plane. It might be from a perspective of an outside observer who's watching something happen. We need to have our coordinate system for this problem. And this is one of the challenges that a lot of kids have. M is for the mathematical phase. We're going to start by writing down the proper equations. We're going to continue to go through and put in the known variables that we have with units. Be very, very specific about keeping the units there. And then we're going to go through and carefully solve the problem step by step. E is our evaluation phase. Does this make sense? I want to look at the problem, make sure that the units are correct, that I've answered the question. First of all, I can't tell you the number of times that I received a paper that only had part of the information, or they gave me an answer that wasn't even part of the question. This is going to be our last time to really go through and look at the units. Did we put the units correctly? Do we have the right units for the answer? Okay, there are a couple of pitfalls that seem to plague physics students. The first one we're going to call formula fixation. It's the incredible desire that they want to jump to the first formula that they can find and put the numbers in it right away and go for it. The reality is physics is not about memorizing formulas. It's about applying concepts. The second major pitfall we have kind of ties in with that first one, where they're rushing to calculate. And one of the places I love to see this, when I pointed out to my students, was doing a problem with a car going around a curve. And they're asked, what is the maximum speed the car can take this curve at? Well, they all freak out because they rush into doing the math on it and realize they don't have a variable. And there's no way to get that variable. But because they've insisted on putting numbers in immediately, they miss the fact that the variable is on both sides and cancels itself out. So take some time and hold off on putting the numbers in. The next pitfall is, again, something that I think is primarily a physics issue. I don't see it as often in math students. And that, I think, is because math is set up in a way where if we're dealing with a circle today and tomorrow's a triangle, we don't worry about what the circle was. In physics, both of those concepts may be called upon in the exact same problem. So it's imperative that we don't try to limit our scope to just one little piece. We have to see the big picture. We have to see how everything connects. Another thing that people tend to have an issue with is when they get into making assumptions. We can make certain assumptions in physics that don't necessarily occur in everyday life, but we can come very close with an approximation. One of the biggest ones we talk about probably is the idea of having something that's frictionless. We know there's no such thing as a frictionless surface or a frictionless bearing. But because we've got technology that has put things to a level that the friction is relatively small compared to the overarching idea, we can assume that we do have things that are frictional. And the biggest pitfall of all, ignoring units. I know, it sounds crazy, but ignoring units can be one of the biggest things that'll screw you up. Why? Let me give you a quick example. In physics, we typically use the MKS system. We look for meters for length, kilograms for mass, seconds for time. And if you take one of those, let's say we want to take the length of something and I measure it as 11 centimeters, and that's what I put down on my paper, and I'm trying to figure out the speed of something, I will get an actual speed, but it may not go into the formula correctly because the next part has a meter involved, and we need those meters to work together. So we have to be careful on making sure that our units are correct. And please, for pity's sake, don't use obscure ones just to confuse your teacher. There's no reason we should be putting velocity in terms of furlongs per fortnight. Meters per second, please. Now, as a parent, you may say, well, how am I going to instill all this? Where am I going to get the information to give them all the guided practice they need, to take care of the pieces that the book is leaving out, to make sure they don't have these pitfalls, to give them the guided practice? How do I do that? I have a solution for you. It's called the Physics Mastery Program. And what this is what this is me teaching the course. Every lesson begins with a simple lecture, and it then progresses through to practice problems. Every student that's enrolled in this program will have access to the Solutions Library membership. So there's where your guided practice is coming from. Coupled with all that, you get me. And what I mean by that is once a week, there's an open office hour. Anybody can come in. We can talk. If you have questions, we can go through those. It gives us a chance to communicate. Okay? It's not just a simple video course. This is actually an interactive course. As with the Solution Library, if you find a problem that you don't know how to solve and you're having issues with it, you send it over. We'll make a video on how to solve that problem, or actually a parallel problem, but you'll get the idea. You can follow along. There's the guided practice. As we go through these problems, we will actually go through and model each of the steps we've talked about, taking your student from being a novice problem solver to an expert problem solver. I think you'll find this very beneficial. I think any homeschool student, co-op student, that you're trying to do physics, this is a great resource. If you'd like some more information, check the link below and it'll take you to our website, and we've got everything outlined there. You can actually see some of our an example of one of our classes. You can see how we do some of the guided practice work. It's all there. Physics doesn't have to be the course. Physics doesn't have to be overwhelming. With the right technique, the right approach, your student can thrive. Join the Physics Mastery community now and watch their confidence grow with every lesson.